Let me start with any questions from students from Bhopal. Pune, please be ready. Any questions from Bhopal? Yes, ma'am.
The practice set and question number 3, it was like, what are the resonance for isobutane?
Yeah.
So it would be 2, right?
Why?
Because there's one middle carbon.
Right.
Which has hydrogen.
So unfortunately, I was thinking of isopentane and I gave the answer for isopentane. Yeah, you're right. There'll be 2 resonances.
The answer was showing one.
There you go. So this is exactly why I'm happy that you tried and you've spotted the error. Okay, let's revisit what we saw yesterday. We were looking at definition of spectroscopy. We defined spectroscopy as the interaction of light with matter, where light is the source that you end up applying, and the matter is the molecule or the system that you want to study. And when you end up disturbing the system, you get information, and that information is what you want to analyze. And this is what would give you the characteristics of the molecule that helps you understand how to distinguish one molecule from the other. Okay, so this is the overall outlook of what is spectroscopy. Okay, so with that being the case, we moved on to define what is NMR spectroscopy. NMR spectroscopy uses radio frequency waves to perturb your system. Perturbation is a disturbance. If people are not able to understand this, whenever you are having fever, what do? You put a thermometer up to check what is your body temperature, right? In theory, the thermometer absorbs a small amount of heat in order to measure your body temperature, correct? In fact, that is a perturbation. That means it takes heat from your body. Is that true? So it is disturbing the system that it's probing. But the mere fact that the amount of heat it takes is so small that you assume that it's not much of heat taken. So in theory, every measurement is a perturbation. Every measurement is a disturbance that you cause. And spectroscopy is an example of it. Think about it. Your quizzes and exams and practices are a perturbation. You're not happy taking them, correct? But at the same time, unless you get disturbed and you think about it, you don't get to the answer. Everything is a perturbation. So spectroscopy is one such where in NMR spectroscopy, you apply radio frequency waves and try to look at, okay, what comes out of it to understand what the system is. Yeah. With that being the case, now let's go into a little bit of details. Let me see what else I did yesterday. Yeah, so we were talking about energy levels. So let me dive a little bit more deeper into this whole thing. So when you're having, let's take the proton atom, for instance. There are some elements in the periodic table that are NMR active. So how does one get to, guess whether a nuclei is NMR active or not? That depends upon the mass number and atomic number. Mass number is the one that determines the overall mass, and that's driven by the total number of protons and neutrons that are being present. People who know a little bit more of physics know that protons and neutrons and electrons are not the basic particles. There are even more subdivisions of particles called quarks and so on and so forth that have their own characteristics of spin and mass. If you think about it, proton has a mass. Does neutron have a mass? Yes. Yeah, neutrons have a mass. How about electrons? Electrons have a mass. Yeah, but it's about 3 orders of magnitude lesser than that of a proton, correct? So protons and neutrons put together gives the mass, and you can kind of, approximate. Electrons don't end up giving a mass, and therefore the mass number is decided by the total number of protons and neutrons that are present. In order to maintain electron neutrality, the number of protons and number of electrons have to be constant, which is what is the atomic number, right? So when you're taking 1H, you're talking about 1H1, where the one at the bottom is the atomic number, while one at the top is the mass number, right? And proton is known to have a spin quantum number of half. So please be careful of what I'm trying to define. Nuclear spin quantum number. This quantum number is in addition to the other quantum numbers you have been exposed to in quantum mechanics, namely N, L, M, and MS quantum numbers, right? If you recollect the quantum mechanics or even the basic chemistry that you have learned, you know that N is the principal quantum number. And what is L? The azimuthal quantum number. The M, the magnetic quantum number. And MS is the spin quantum number for the electron. Nuclei also have their own spin. Remember, the I quantum number we are talking about is restricted to the nucleus and not to the electrons or anything else. Okay? So the nucleus also has its own quantum number called the nuclear spin quantum number. And this is something that has to be non-zero. So basically, I has to be non-zero to be NMR active. And the most abundant nuclei that we end up probing is the proton nuclei, and we said it has a spin quantum number of half. The best part of whatever we want to use from here on is that you've already learned in quantum mechanics that if you have a certain quantum number m, ms is going to be given from minus m plus 1, and so on and so forth, m minus 1 until m. You guys remember this? It goes from minus m to plus m with integer units of 1. The same set of rules also apply to nuclear spin quantum number. Okay, so when you have nuclear spin quantum number of I, let's call the projections of it as Iz will go from minus I plus 1, so on, I minus 1 to plus I. Yeah, so this is kind of nice and easy, right? So let's take an example for spin quantum number of half for the proton nuclei. What are the allowed values of Iz? Of course, you have to start with minus half, and then you go minus half plus 1, which already takes you to plus half, which is the other extreme, right? So for a nuclear spin quantum number of half, you're only going to have two possible states, which are designated as minus half and plus half, which is the Iz projection of the quantum number. Make sense? Okay, we started with trying to understand what is the role of the mass, atomic number and mass number to predict whether an element in the periodic table is NMR active or not, correct? Yeah. So let me take another example. Let's take the next isotope of proton, hydrogen atom, which is the deuterium, right? And here, if you're able to see, you have an even mass number and an odd atomic number. Yeah. These kind of nuclei are known to have an integer nuclear spin. In this case, the I for deuterium is equal to 1. So therefore, the allowed values are going to be minus 1 plus 1, 0, 0 plus 1 plus 1. That is the other extreme of the quantum number, right? So how many states are possible for a nuclear spin quantum number of 1? You're going to have 3 possible states. Does that make sense? Yeah, good. So let's extend it even further. What is the next isotope of hydrogen atom? It's a tritium atom, tritium, right? This is an odd nuclei, which once again goes back to, if I remember right, spin quantum number of half. Okay, so overall, slowly you're able to, I'm not proving anything, I'm not deriving anything. I'm just trying to give you an idea. Let's take some more examples. Let's take one of the most important elements that we will try to see across chemistry and biology, which is carbon-12. Okay. And for instance, the other super essential atom in life is oxygen-16. Okay. Whenever you have an even nuclei, the spin quantum number is 0. This is extremely important to remember. Okay. Whenever you have an even nuclei, you have no spin quantum number associated with it. That means these are NMR inactive. Does that make sense? Yeah. Of course, this is still more. I'm not trying to prove anything. I'm not trying to help you derive how this comes up. If you want to understand how this comes up, you have to understand what are protons made of, what are neutrons made of, basically quarks, which quarks put up together to give a spin, and so on and so forth, and understand how nuclear orbitals are working and so on. I think that complicates things to an extent which I don't want to worry about. All I want to tell you is that the nuclear spin quantum number is a property of that given element. If you accept it as a property, then we can move on. Yeah. And there are ways to predict this property, but that's not what concerns us in this course. So therefore, we are not going to worry about it much. Does that make sense? Yeah. So let's take another example where you have 13C6, right? This goes to be an odd even nuclei, right? Yeah. So these guys end up having a nuclear spin quantum number that's non-zero. So therefore, anything that's NMR inactive, you will always find an isotope, which would be NMR active. I request you guys to go back and see what is the spin quantum number of C13. Maybe I'll show you as I go forward. Let me go to the last part of it. Let's take another element that's super important, which is nitrogen. The most abundant isotope of nitrogen is 14N, right? And this is an even odd nuclei. Is that right? Now, if you take a look at the even odd nuclei, the spin quantum number of this is going to be, just had an example of that a moment earlier. It's a very similar system like this, isn't it? Yeah. So this, if I remember right, has a spin quantum number of 1. All right. So slowly what you're able to realize, every possible combination, you would slowly understand, okay, which will have an NMR active spin, isotope, and which will not. The reason why NMR is a super important technique for chemists and biologists is that this is a periodic table that you're able to see. The interesting aspect is that except for argon, cerium, you realize that there is a color associated with every element in it. Pink is spin half, and yellow is any n/2 spin, and green is any element with spin quantum number that's n. You'll see that some color is associated with each of the element, indicating that almost every element in the periodic table, except for argon and cerium, is NMR active, at least has one isotope that's NMR active. So this is why NMR is such an applicable technique that you will somehow find a way to look at it without disturbing the system, meaning that the elements are by themselves. You don't have to add extra probes. For instance, if you want to probe fluorescence, you need to have a fluorescent probe that will exist, but you don't have such complications with NMR. NMR finds its widespread application across chemistry and biology because you will at least find one isotope of every element that's NMR active. We just started with a proton. For most part of this course, we will concern ourselves only with nuclear spin quantum number of half. We will try to understand as the lectures go today and tomorrow why that is the case. But for now, let's dwell more into the spin half system. And the allowed values of this is going to be plus and minus half, right? Okay, so now this, having said this, the next question that we want to ask is, you have two energy levels for spin quantum number of half. But when you keep it in the absence of an electric or magnetic field, these are degenerate energy levels, meaning they both are of same energy. If you guys might recollect, what did we define as spectroscopy? You want to have two energy levels that are spaced from one another. You can only do spectroscopy when you have quantized energy levels that are separated from one another, right? But unfortunately, yeah, you said it's NMR active, but in the absence of any magnetic or electric fields, you have no separation that comes between the nuclear spin states. That's a problem, meaning that therefore you can't do spectroscopy. Interestingly enough, what happens here is that if you try to understand the energy equation for magnetic dipoles, people who might remember, it's going to be given by minus mu dot d. Is that correct? Where mu is the magnetic? Yes. And B is the external magnetic field. So what you are able to immediately realize is that if we have a given magnetic field, then things could start to change, provided you have a magnetic moment, right? Interestingly, the magnetic moment is proportional to the spin quantum number. Yeah. And this proportionality constant is given as gyromagnetic ratio. You might immediately ask, I put a vector symbol on the left, why didn't I put on the right? It actually goes on to the nuclear spin quantum number. Yeah. So what are the components of the nuclear spin quantum number? The I vector is going to be given by IXI plus IYJ plus IZK. Okay. And what did we say is the gamma? Commonly referred as gamma. It's called the gyromagnetic ratio. If you have I that's non-zero, you have a magnetic moment. The instance you have a magnetic moment that's non-zero, you realize that if you put in a field, therefore it's going to have its own energies. Correct? So the magnetic field that we are trying to apply let's assume that we apply along one axis. Okay, so basically you have 0 times I, you don't apply along the X or Y axis. Let's say you apply along the Z axis. Then you might ask, okay, what's a Z axis and what defines a Z axis? Whichever direction you apply the magnetic field becomes a Z axis. Okay, we can always have a frame of reference and we choose the direction of the external magnetic field to be the Z axis, and the magnitude of the field that you're applying is given as B naught. Yeah. So therefore, what is going to happen when you have E is given as minus mu dot B, it immediately translates into minus gamma I dot B, which immediately, since you're applying only along the Z axis, minus gamma H cross B naught IZ will start to come, right? Each of this is of course, I can't put a vector on top of it because it's no more a vector, you've taken the dot product, right? But it'll actually pick the Z component of the spin state you're trying to look at. Yeah. So therefore, what we are immediately able to understand, yeah, a given spin half has degenerate spin states of plus and minus half. But the moment you apply an external magnetic field of B naught, depending upon the IZ quantum number, there will be splitting that starts to happen. Okay, I'm not committing on whether plus half is the ground state or minus half is the ground state, which we will see in a moment. Is that clear for everybody? So therefore, what is going to end up happening? The energy is going to be given by the IZ, the Z projection of the spin state that you're trying to look at. Correct? Yes. Yes, I'm able to hear.
Where did the H cross come from?
Actually, H cross doesn't come here. I'm sorry. H cross comes after you end up applying it on the spin state. Thanks for getting this thing into this. If I'm right, yeah. H cross comes after you apply IZ on the spin state. Okay, let me write that. Good that you pointed it out to me. I square and I comma M. So this is the Dirac bracket notation. I'm using the ket state I comma M, where I is the nuclear spin state and M is the projection. I am switching between Z and M, but because M nicely works out for us as chemists, I into I plus 1, and it gives back I comma M. Of course, see, this is exactly where I make a mistake. As NMR spectroscopists, we keep losing the H cross because we tend to set H cross equal to 1 at some point. Okay, so please be aware, if you set H cross to 1, remember that the units won't match if you don't write the H cross. Okay, but we are going to routinely do it that we'll forget H cross exists. H cross, you can imagine as the unit of the quantum integer. This thing, that's the smallest step that's even possible. Okay, if you set that to 1, it's like a unit vector. You forget that the unit vector exists. Correct? So it's something of that. So thanks for raising this to me. I generally make a mistake here. IZ of I comma M is going to be given by M H cross I comma M. So basically what we are trying to say, the functions I comma M are eigen functions of the operators I square and IZ. So what did we say? The energy is going to be given by minus gamma B naught IZ, right? For any given state that we are trying to look for. So let's try to apply it for E for a given M. So that's going to reduce itself to this. Here is where the H cross starts to come. You're going to have the M state that's going to be present. And M is going to be between minus I plus 1, and so on to I minus 1 to plus I. So now, let's say we take spin I equal to half. The two states that you're going to have is E half and E minus half, right? And then what's going to end up happening here is that E half is going to be minus gamma H cross B naught by 2, and E minus half is going to be it's not by 2. Correct? So these are the two states. It's very tempting for people to say, therefore, E half will be the ground state. Yes, it is indeed true under the assumption that gamma is greater than 1. Okay, where gamma is the gyromagnetic ratio. So let me rephrase it for
0, right?
Sorry?
Gamma greater than 0.
Yes. What did I say? Sorry, that's right. Greater than 0. So proton, you're able to see is that whichever has a spin quantum number of half, right? And its gyromagnetic ratio is given by 2 points, I think 6752 to 10 power 8, I think, per Tesla per second. This is the SI unit that is used. Okay. And you're able to realize, okay, for proton system, what is going to happen when you have I of half, you're going to have the ground state as half comma half and the excited state as half comma minus half. Right? Makes sense? And then, of course, if you take the delta E between the states, which is going to be E minus half minus E half, that's going to be gamma H cross B naught. This energy difference is going to be gamma H cross B naught. Right? So there are a few very important messages that you get out of this. What are the messages? Delta E is proportional to gamma, meaning that as you have a nucleus that has higher and higher gyromagnetic ratio, the energy levels are farther and farther away. Or on the contrary, for lower and lower gyromagnetic ratios, the energy level starts coming closer together. We will see the implications of it as we go forward. Okay. Delta E is also proportional to B naught. Indicates that if you have higher and higher magnetic fields, you can separate the energy levels more and more. Okay. Or rather, if you have lower and lower fields, you're going to have smaller and smaller separation. Right? Okay. Of course, this is assuming gamma greater than 0. If gamma is less than 0, the only change that happens is that the minus half state becomes a ground state and plus half becomes the excited state. Okay. The energy difference would still be gamma H cross B naught. Okay. Which is what we call as the Larmor precession frequency, omega naught. But I'm not going to define it yet because it will come up with a minus omega naught and it will confuse you guys for the time being. Let's not go there. Textbooks are also quite confusing on whether it's a 500 megahertz or a minus 500 megahertz, but let's not go there right now. But the important message you guys are able to understand is that if there is an element that has a non-zero nuclear spin, when suspended in an external magnetic field, would have their eigenstates that are separated by a given integer unit. Yeah. One of the homework I want you guys to exercise that I want you guys to think about is that for spin 1, how does this look? Of course, you can always ask, can there be a spin 3 by 2? Yes, there can be. Oxygen 17 is a spin 3 by 2 system. Anything that has a spin quantum number greater than half is called a quadrupolar nuclei. Quadrupolar implying you just not have magnetic dipoles, you just don't have a mu. In addition to magnetic dipoles, you will also have electric dipoles. That makes it a quadrupole, nuclear quadrupole, because you have dipoles from magnet behaving like magnets and behaving like electron dipoles. Therefore, you have a quadrupole. Unfortunately, these are little tougher systems to study for reasons which we'll learn later on. This is another reason why I said we will restrict in this course predominantly to spin half systems. Okay, I'm sure as chemists or physicists, you will also be able to understand if the spin quantum number starts to go more than half, you have more than 2 states that are present. More than 2 states that are present, population is going to get distributed across these states and therefore reducing the population difference. More the population difference, more the sensitivity of spectroscopy. So therefore, that's why spin half systems are the most accessed in NMR. Make sense? Yeah. If you're doing NMR of spins greater than half, it's called NQR, nuclear quadrupolar resonance spectroscopy. Any questions thus far? What I have established so far is that if you have a nuclear spin quantum number, the degenerate energy states can be split if you suspend it in an external magnetic field. And the energy difference between the ground and excited states are proportional to the gyromagnetic ratio and the strength of the external magnetic field that is applied. I tend to follow textbooks that are prescribed in the syllabus. This is from the Kavanagh textbook. And this is an important table because it gives an idea of some nuclei. What is a nuclear spin quantum number? What is the gyromagnetic ratio? And what is the natural abundance? Natural abundance matters because if you have less concentration, you're going to have less number of nuclei that's going to be NMR active within a given volume, right? So let's start with our favorite nuclei, which is proton, 1H, which has a beautiful spin quantum number of half and has one of the highest gyromagnetic ratios. I'm saying one of the highest gyromagnetic ratios, not the highest, because on record, tritium, which is the isotope of proton, has a higher magnitude of gyromagnetic ratio than 1H itself. Okay, but do you guys know why we don't use tritium for NMR? Yeah, abundance is one problem, but apart from that, right? So tritium is a radioactive element. Okay, it's not very safe to do, right? So proton is the most accessed because, as you guys rightly said, it's spin half, has one of the highest gyromagnetic ratios, and has a 99.99% abundance. So this explains why chemists love proton NMR. Actually, the most accessible across all elements that's feasible in the Earth, right? And every chemical element that you work with has a proton attached to it. Very few compounds don't have a proton attached. You're able to see deuterium has a spin 1, which I told earlier, and is about, say, 1/7 of the gyromagnetic ratio, has a much lower abundance. We'll come back to deuterium. Deuterium is also a very important isotope in NMR in addition to proton, but we will keep that discussion for a little later. C13 is a wonderful nucleus, yet again spin half, and if you go back and calculate, you will realize that it is about 1/4 less in gyromagnetic ratio than proton. Okay, 1/3.98 or something like that, 1/4 of the gyromagnetic ratio. And more importantly, you will realize that this 12 carbon, which is the most abundant isotope, is also most commonly found, right? So 13C is only about 1% of natural abundance, meaning that, okay, in addition to the fact that the gyromagnetic ratio keeps the energy levels closer, therefore lesser in sensitivity, on top, it has a concentration issue. That's why if you run a proton NMR for 15-20 seconds, you have to run the carbon 1D NMR for about maybe 15 minutes or 30 minutes or 1 hour or so on and so forth, right? We'll see more of why the energy difference results in lower sensitivity later on. N14 is a spin 1 system. It has a certain gyromagnetic ratio. I'm just going to skip it, but except for the fact that it's one of the most abundant nitrogen nuclei. But the nitrogen nuclei that we like the most is N15, which has a nuclear spin quantum number of half. Most importantly, it also has a negative gyromagnetic ratio. So be aware of the fact that when you start speaking about the ground and excited spin states for different systems, it could be quite, things could just reverse. Okay, it's not going to change any of the observations that you're going to do except for a few experiments. For generality, about 90-95% of the time, whatever we end up discussing for proton will work for this. Of course, the negative aspect of it is that it's just 0.4% abundance. Yeah, especially being that we are biomolecular NMR spectroscopists, we like to see proton, carbon, and nitrogen. So these are the 3 nuclei that we try to look at. Coming from a nucleic acid background, I also like phosphorus, which is also spin half. And if you slowly pay attention, it's actually one of the most sensitive nuclei after proton. Of course, there's also fluorine. People love fluorine as well. Fluorine is probably the 3rd highest in gyromagnetic ratio. First is tritium, next is 1H, then is 19 fluorine, and there are maybe something in the middle, but then phosphorus comes next. But phosphorus is fantastic because it's also 100% abundance, right? When you look at nucleic acids, it has a phosphate backbone, and therefore this is also a very important nuclei to look at. Yeah, so what I request you guys to do is to go back and look at different elements that are part of the periodic table. Bore yourself with what are the gyromagnetic ratio, what is the spin quantum number, what is the abundance, and that will give you an idea of whichever elements you guys want to study, how feasible it is to do with NMR. One other point that I wanted to drive, and it slipped my mind, is that proton to nitrogen 15 is about 1/10. Okay, these are numbers that are good to remember. Why am I saying this repeatedly? Because your mu is going to be given by gamma I. Okay, what is mu? Mu is actually a vector. Basically, it's a dipole moment vector. Just for the sake of it, if this is the dipole moment vector of proton, for nitrogen, the dipole moment vector is going to be 1/10. And remember, in the opposite direction, because the gyromagnetic ratio is negative, right? And for carbon, it's going to be 1/4. So this is going to be for carbon 13. These are vectors I'm trying to give you a picture of. We're trying to get you, the longer the vector, the more sensitive the experiment is. So therefore, as a gamma starts to go lower and lower and lower, the sensitivity starts to drop. Yeah. In addition to the abundance, right? If you have to factor in the abundance, this is about do times 100, do this about 0.4 and do this about 1. Yeah. So you're able to see why proton has so much interest when it comes to chemists. Quickly skip to the next step, which is where we will stop for the day, is to ask, now that you have two energy levels, which is half comma half, for all practical purposes, I'm going to assume the gamma is positive, but all whatever I'm defining works for gamma negative also. Okay. And in general, the half comma half is generally denoted as the alpha state. The half comma minus half is denoted as the beta state. It's just a convention, right? Let's ask one important question here. Okay, you defined these elements or the spins as magnets, and you are suspending it as in an external magnetic field, B naught, correct? From all your classical understanding of magnets, I'm pretty sure all of you have played with magnets, is that when you take magnets to each other, they interact with one another. If you take north to north pole, they repel, south to south pole, they repel, north to south or south to north, they attract. True, right? So therefore, immediately you start to have a question. Okay, you have nuclear magnets, they're very, very tiny magnets, and you're putting in a very big magnetic field, right? So therefore, they have to interact with one another. What is the orientation of these nuclear magnets with respect to the external magnetic field? So that's the next question we will try to understand. So this is the z-axis, x-axis and y-axis. Almost always, whenever I'm drawing a Cartesian coordinate frame, we'll be talking about the right-handed coordinate frame in NMR, which is this way of x, y, z. Left-handed will have y being opposite. I'm not going to define this ever again. Let's say you're applying the B naught along the z-axis, right? So now let's take a look at one of the spins. So remember, whenever you have a bar magnet, what is the most stable configuration of the bar magnet with respect to Earth? Parallel or anti-parallel? Here is the energy minus mu dot B. What is minus mu dot B? It's going to be minus mod mu mod B cos theta. Correct? Now, you want to have the lowest of energy. So what should be theta? Should theta be 0, 45, 60, 90, 120, 135, or 180? Was that? 0. So that what should be the orientation of the magnet with respect to the magnetic field? Yes. So the most stable orientation is parallel orientation. Correct? Similarly, we would tend to assume whatever has the lower energy would be the most stable orientation, right? For some purposes, let me write the alpha state is oriented at an angle with respect to the main magnetic field, right? These are not classical magnets, so they're not going to align parallel or anti-parallel. They're going to align at an angle. So that's what we are trying to interrogate right now. So this is alpha state. Why did I put more parallel to be the alpha state? Because you realize that it should be close enough to the classical magnetic field. So therefore, it has to be as parallel as possible. And the beta state is going to be the opposite state, meaning that with respect to B naught, the more stable state will be as close as parallel as possible. Okay. Now, what is the length of this vector? That's going to be given by I, correct? And what is the projection of the alpha state? That's going to be given by Iz, right? For spin half, we said I square on, let's say, alpha state is going to be given by half into half plus 1, and it'll give back alpha, correct? Because it's an eigenstate. Did you realize that I missed h cross square? So we always write in units of h cross. So forget h cross is going to exist from here on, right? So this is going to be half into 3 by 2, which is going to be 3 by 4. So therefore, I is going to be equal to square root of 3 by 2. So the length of this vector is square root of 3 by 2, right? For spin half, what did we say is the projection? The projection is going to be plus half. True? So therefore, the angle theta is going to be given by, what is this going to be? Tan theta is going to be given by 1/2 over root 3 by 2, which is going by 1 by root 3. Therefore, theta is tan inverse of 1 over root 3. Yeah? Sorry. Thank you. Thank you. Thank you. Yeah. Yeah. Sorry. Right? What is cos theta 1 over root 3? If you go back and take a look at it, you're going to get something like 54.7 degrees. So what do we understand from this? The nuclear magnets do not align parallel or anti-parallel to the external magnetic field. They align at an angle with respect to the external magnetic field. Yeah. I request you guys as an exercise to work it out for spin 1 system. What are the angles that are subtended for a spin 1 system? Okay. And then slowly start to imagine, as you increase the spin quantum number, how many states are going to be there, how many orientations start to come. Tomorrow, what will we be looking at? We'll be looking at the population difference between alpha and beta state, and trying to understand what is sensitivity in an NMR experiment. Yeah. So if you guys have time, try to work out the homework I gave, go recollect the lecture I've just given. Thank you very much.